Sorry I can't go back. It just takes a little long, but I think you'll be able to follow it in the book. In fact, this is the end of it right here. Okay? And, this table's pretty good. For n equal 1, they gave us x of 1 would be 1. F of x of 1 would be minus 1, just like we did. By the way, the function is x squared minus 2, so that certainly would be f of 1, f of 1. Okay? F prime is 2x, so that would be 2. And then this over that would be a minus 0.5, and x of 1, which is 1, minus 0.5 is 1.5. So we're closer to the answer right there. Well, not actually, we're a little, no, yeah, we're closer. Okay, then we plug in this and do f of n, which is 0.25. 1/4 is what we said. And then we found that to be 3, I hope. I don't remember now. Yes, I believe that's right. And then the 1/4 divided by 3 was 1/12, which happens to be that, carried out to a few decimal places. And then this plus or minus that gives you 1.141667. Then taking that as your x of 3, figure out what f of x of 3 is, and we rounded a little bit there. And f prime of x of 3, that should not be a 4. Okay, the calculator is running into its own limitations here. That should be 8.833333333. Yeah, but we'll let them get by with that. And then the ratio of that to that is going to be pretty small. That you subtract from here, and you come out with that. And why don't you give me exactly what square root of 2 is again? .414. I just don't remember the ones past that. 3.5. Okay. So you see 2, 1, 2, 3, 4, 5, 6, almost decimal places. We are that close. Probably one more iteration would be within the measure of your calculator, okay? Because we're getting there very, very quickly. In fact, when you do, if you happen to have a graphing calculator, say find the zeros, this is the method it's doing electronically. Doing it much faster than we were, but that's what it's doing. They haven't found anything faster, I don't think, than Newton's method. All right, good deal. Sorry about forgetting to turn on the recorder. Thanks for catching it. Of course, in this case, you know there are 2 zeros, plus or minus root 2. And to 6 decimal place, that's what they give it. They got 6.21, last 3 digits 216. We got 214. Okay, and so after only 3 iterations of Newton's method, you have attained an approximation within 2 millionths of a value of the actual root. That's not bad. Okay. The first iterations is shown here. You started with x equal 1 here, went down to this, and then got the second iteration up here, 1.5. Then you would have gone up here to that value, done a slope of that. It takes you back to here, and you see you're on top of it in no time. Okay. First iteration of Newton's. Okay. All right, let's back up now and do example 2. Now, they don't have it in the slide set, but if you go to larsoncalculus.com, you can see an interactive version of this type of an example better than the PowerPoint. So let's use Newton's method to approximate the zeros for f of x is equal to 2x cubed plus x squared minus x plus minus x plus 1. I can't say one thing and write the other. Okay. Continue the iteration until two successive approximations differ from less than 1/10,000th. Okay, so we're going for our e of less than 0.0001. The difference between the two. How's that? Okay. Now they don't tell us where to begin. Okay. A real easy thing to do is to determine that when x is equal to 0, what is alpha? 1. Okay, because those three are all 0. Another easy one to do is when x is equal to 1. That would be 2 plus 1, 3 plus 1, 4. Well, that adds to 0. That's 3. So let's go backwards maybe. Okay, x equals minus 1. This will be a minus 2 plus 1. That would be minus 1. And that would be, oh, that's a plus 1 and plus 1. So that's plus 3. So we know there's a 0 in between minus 3 and 0, right? 0, this is positive, minus 1. Yes.
How are you doing?
Yeah.
I was trying to see when I talked to you after class.
Yeah, okay. I'm out of this class at
11:40.
11:40. Yeah.
All right, thanks.
Okay. All right. So we know there's a 0 between 0 and minus 1. Everybody saw how we did that. Just plug in some x's, and as soon as you get one positive and one negative, see, well, first we plugged in 1 and then went to a 0 and then 1, and you got more positive. No zeros, well, we don't know there's no zeros there, but no guarantee of a 0 there. We're going to go 0 to minus 1, and minus 1 is negative. You know there's got to be a 0 there. So I would have started, oh, they have a graph here. Oh, I must have missed it. Let me go back and do my calculation again. That would be a minus 2. Oh, I did mess it up. Minus 2 plus 1 is minus 1 plus 1 plus 1. That's still positive. You have to go to minus 2 to do it. At minus 2, this is minus 8, minus 16. That's definitely going to do it. Whatever the rest of them are doing, that's going to be a negative number. So that would be plus 4, minus 16, plus 4 is minus 12, plus 2, plus 2 is minus 10, plus 1 is minus 9. So yeah, definitely there. I botched it. But I bet you it still would have worked, okay? So therefore, it doesn't matter. I think I would have started at minus 1. They start at minus 1.2. And I guess they drew the graph and said, that looks, minus 1 would get you there too, but they started at minus 1.2, so let's do it. So x sub 1 is equal to negative 1.2. All right. Now, what else do we need to do? Take a derivative. I wonder when you're going to wake up. Okay, never mind. Okay, then what's that? Second? 6x squared plus 2x minus 1. Okay? Now, I'm going to ask y'all to do the calculators here because it's going to be a bit much to do it. So there's your x sub 1. We're going to start with our x sub 2. X sub 2 is going to be, where do we begin? Do I need to write down the iterative formula again? Some of you just came in. Let's do it. X sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So, this is x sub 2, so we start with our x sub 1, which they gave us, negative 1.2, minus, let me write it down, negative 1.2, minus, now what you have to do is plug in negative 1.2 here, f of negative 1.2 1.2, okay? So 2 times negative 1.2 cubed plus negative 1.2 squared plus 1.2, because it's minus a minus, plus 1. What's that numerator? 0.184, okay, over, and then plug it into your f prime. So it's 6 times negative 1.2 squared minus 2.4 minus 1. 5.24, okay? Do that calculation, and what you get your x sub 2 to be. Now, time out, just a moment here. This is a little bit of a warning here. Look at what our error measurement needs to be. 4 digits after the 0, okay? So therefore, to round off the 3 here is going to set us up for failure to begin with. And around the 2 is probably going to ensure we get there to fail quicker. Okay, so we really need to carry, I would say, 1 more digit than what we're going for. Because at the end, we've got to subtract the 2, and we're not going to quite have it. Now, this is exact, okay? They gave it to us. Were these exact too? Oh, they were. Okay, fine. You're right. Okay, I thought you were rounding off for me. Okay, and what does that give you then? 0. The whole thing? 0.035. Are you doing just the subtraction, or are you doing the whole x of 2? Okay. I was going to say, I'm feeling real bad about this process if that was that. I think it's still going to be 1.2. Well, these calculators sure are slow, aren't they? Before I saw hidden figures, I always thought calculators were black boxes. But then I realized that's what they called the people who did the calculating were calculators. I was talking about the black boxes, of course, being slow. What do you get?
Negative 1.235.
225. 235. Wait. Start over. Ah, my pen didn't erase. Okay. 1.235. Okay, that'll be enough, I think. Yeah, I think that'll be enough. All right, that's going to be our x of 2, so our x of 3 is going to be negative 1.23511 minus, we have to plug that into our L. Now, do any of you ever do any computer programming? All right. It's really not too hard to do. What you do, well, depending on what package, it's been a long time since I did it. You just set up a function, subroutine, and you define that to be the function, this to be the function prime, okay? And then as soon as you send it to it, you send it to it with that value, it spits it out. Y'all have to do it by hand, unless I can get y'all programmed better than that, but no, never mind. What's your function value at negative 1.23511? Plug that in here. 2 times negative 1.23511 cubed plus negative 1.23511 squared plus 1.23511 plus 1. Anybody? Oh, where's the function mode key? No unplugging, huh? Or if you want to just give me the whole caboodle, that would be fine with me too. Anything would be good.
.0077.
That's the top, okay? 0.0077. We do need a few more digits. Huh? Do you have any more on your display? Okay. Because, frankly, what happens, since y'all are working, I won't interrupt it too badly. I may. When you start subtracting digits that are fairly close to each other, you wipe out a bunch of digits, okay? And therefore, your number of digits are just what's left over at the end. Now, these aren't going to be that close, but that's why you always have to carry a few extra.
.0077.057.
Okay, that's probably going to be enough. Over. Now do the same thing for f prime of that. 6 times negative 1.233511 squared minus 2.47022 minus 1. Whatever. I'm guessing that's going to come up with even a larger number. Pretty exciting stuff, though. Huh?
5.68.
Say again. 5 point what?
68.
6827
6.
6. That probably is enough. Okay. Did you round that last one?
Yeah.
Okay, good. All right. Then do that calculation. Our x4 would be about like watching water boil, isn't it? Or paint dry. Okay.
Negative 1.23.
2.3. Say again. 2.3. 365. Okay, we must have had an error somewhere because they have 3375. So we may have not carried enough digits somewhere out there because we got off a little bit. But once you got that next one, 3375, then you do it one more time and you're still right there at negative 1.23375. Well within your error bound. Okay, this one wouldn't have quite been there, 3355. That would have been just a little bit more than 1 to the 4th place. Well, actually 1 to the 3rd place. So quite get there. But Newton's method works. Sometimes our calculators don't. And you have to carry, in fact, my recommendation, if you have a calculator with memory on it, as soon as you got one of these values, store it, okay? And then you can come back and use it again and again. And that way you're carrying all the digits that you have available, okay? And even when you're doing these calculations with those, as soon as you get that calculated stored, if you have multiple storage places, remember where those are being stored. And then once you've used it, you can store the next one on top of it, because it's the same procedure. That's basically what a computer is doing for you. It's remembering that and then not having to calculate.
What it was, the top value is supposed to be negative.
A minus is should be a plus. Yeah, that would have done it. Yeah. Okay. Those little signs are there to trip you. That's the only purpose in life, is to trip you. Okay. Especially the minus signs. Okay. Now, what we say here is that the function converges. Newton's method converges. So let's hit the next slide. We'll just go on past this. When, as in example 1 or 2, the approximations approach a limit, the sequence of approximations x1, x2, x3, up to x and n, or wherever, is said to converge. Moreover, when the limit is some value c, it can be shown that c must be the 0 of f, or a good approximation of the 0 of f. Newton's method does not always yield a convergent sequence. One thing you have to avoid is first derivative equals 0. That's never going to converge anywhere, because it's never going to intersect the x-axis at all, because it's parallel to it. Okay? So this is one way that it messes up. Okay? Let's see. There is another way. If you had chosen up here to be the first one, then you would have pointed down here. And if it gets past the 0, then it will converge. Okay? But if this turns over and does here, then you're going to point towards some 0 back here. You'll never find that one. Okay? If this does indeed do some sort of weird thing out here. And if this were to keep going up and then you point down here, and you're still this side of the 0, you may or may not find it. Because if you land on that, you'll not converge. If you keep landing on this side of it, I don't know if, there are some other situations where Newton's method doesn't work. But if you know approximately what the answer is, it'll get there, and get there pretty quickly. Because Newton's method involves division by the first derivative, very clear you can't have the first derivative equal 0, okay, in any sequence. When you encounter that problem, you can usually overcome it by choosing a different value for your xy. If you know about where that 0 is, get a little closer maybe. Another way Newton's method can fail is shown in the next example. Oh boy. And this one, I think you see what a problem will be here. Well, let's do it. What would be your approach to that if you were going to try to pick a 0? What would be your first step? The function f of x equal x to the 1/3. Okay. Time out before you even do that. Do we know what a 0 is?
0.
Yes, x equals 0, that starts at 0, right? Okay, so point 1 looks like a pretty good choice. Pretty close to 0, so let's go for it. What's your first step? Take a derivative. Okay, f prime of x is? A little louder. 1/3 x to the negative 2/3. Okay, good deal. All right. Now, what's Newton's method? It would say x sub 2, that's where we'll begin, is equal to what? 0.1 minus okay. What would go next? F of 0.1, which is 0.1 to the 1/3 power, right? Divided by a 3. Ooh. We're dividing by, and x is to the minus, so the x goes back upstairs, and this would be 0.1 to the 2/3 power, right? I did do that right, correct? When you divide by a fractional form, the denominator, actually the 3 goes up there too, doesn't it? Sorry about that. So the 3 goes upstairs because you're dividing by the first derivative, so that goes upstairs. And then this is also in the denominator of your denominator, so it goes upstairs. So that's 0.1 to the 1 power. So this will be 0.1 minus 0.3, right? Shell game. Shifting too fast? Okay. First, you divide this part. That when you're dividing by a fraction, you're inverting and multiplying. So that 3 flips around to the top, and this x to the negative 2/3 becomes, the x is 0.1. So this becomes 0.1, and 3 times 0.1 is 0.3. What does that yield? Negative 0.2, right? Now, you think that's a good choice. Well, let's see. X sub 3, so far the calculations aren't too bad here, are they? Negative 0.2 minus, okay, now we got to plug in, this will be a negative 0.2 to the 1/3 power, and then you have a 3 here, and 0.2 to the 2/3 power. Oh, that's a negative 0.2 to the 2/3 power. That's a 2/3 power, not 2/2. Okay? So this again would be negative 0.2 minus, now, okay. The first indication something may be going wrong, though it's not a guarantee here, you started at 1/10 away from the 0 you knew, and now you wind up 2/10 on the other side of it. Well, maybe it's going to get back there. Let's see. Can you do the cube root of a negative number? Well, yeah, sure you can. And in fact, the cube roots go away anyway, so it's minus a 3 times a minus 0.2, right? Oh, no. I think that's going to be a plus because you're multiplying them. I think. This really is getting hairy here. But what the point is, you get minus 0.2 minus 0.6, which is negative 0.8. Guess what, folks? We're heading the wrong direction and not coming back, okay? It keeps getting further and further away. Why in the world would that be true? Well, you just crossed when you went from positive to negative here, you crossed a place where the first derivative doesn't exist. So you get on the other side, and it's going wacko with you, okay? So, no, it's not going to work here. There's no way you can get it to work because if you think about it, the first derivative is not defined at 0. So therefore, anything you're doing there is, since you're dealing with that, you're never going to be able to get back to that because even if you got close to it, it's going to infinity there. Now, there's my arm waving, yakking about it. Let's see if they show a better rendition here. Okay, we didn't go far enough, okay, but let's see. There's our f prime, 1/3 of x to the minus 2/3. So x of n plus 1 is that. That's Newton's method. Okay, so we plug in, and that would be, okay, x to the n of 1/3 minus 1/3 x to the minus 2/3, which winds up being x of n minus 3 times x of n. That's the shortcut. That gets us there, okay? So plug in for x of 2, we'll plug in 0.1. So 0.1 minus 0.3 is negative 0.2. Okay, or yeah, there's the real shortcut. And when you do that every time, you get further and further away. We got minus here, and that other one should have been the plus. Okay, plus on that side, then minus on this side, and then plus on that side. You keep getting further and further away, and here's why. Look at what this function is doing. Here is the cube root function. It's the inverse of the cubing function, which would be going like this, which has a horizontal derivative here. This has a vertical derivative there. So when you start at a point here, it takes you to a point over here. Well, that gets you further away. Like I said, that's a bad sign to get further away than your first point was. Then when you go here, you go further away from this one. On the other side, do a first derivative there. You get further here, further there. You're getting further and further away in both directions every time because of a vertical tangent. That's the problem here. Because you never can overcome that. You can't get any closer because that's going to be almost, it flattens out after there, and every point beyond that gets you further and further from the truth. So, nope, that one's not going to work either. So avoid vertical tangent lines, you know. If you got one of those, I wouldn't bank on Newton's method working. And if you get on the wrong side of a horizontal tangent line or on the horizontal tangent line, it's going to take you somewhere else if you're on the wrong side, and it's not ever going to get anywhere if you're on the horizontal tangent line. So those are the two things to avoid with Newton's method. It can be shown that a condition sufficient to produce convergence of Newton's method to a 0 of f is that, hopefully we're not going to prove this one, that the absolute value of f times f double prime divided by f prime squared has to be less than 1. If that will work, that's going to be for any x? I believe so. On an open interval containing the 0. You have to be, this has worked for any x, it's on an open interval containing the 0, where you know it might be. And if you did, no. Okay, and it says, for open interval containing the 0. If indeed it does, remember that last one? The f prime did not exist at 0, so that would not fit the bill. Vertical tangent lines would have thrown you out right there. Okay? Horizontal tangent lines would also throw you out right there. So believe that both of those would have been giving you problems. You have learned several techniques for finding zeros of functions. Zeros of some functions, such as this one, can be found by simple algebraic techniques, such as factoring. Remember how to do that? What would you use on that? Remember the technique? What was it called? Factor by grouping? That was so long ago, of course we've forgotten that, right? Too elementary, Watson, okay? Now this is not a factorization, this is just a grouping, symbols there. What would you do to the first one? First group? Anyone recall? It's called factoring by grouping, so what do you think you might do? Factor, okay. What would you factor out of the first group? X squared, that leaves you a x minus 2. In the second group, all I would suggest factoring out was the minus sign. Minus 1, and what does that leave you? X minus 2. And now you're a happy camper because you got a common factor there of x minus 2. So factor that out. And what do you have left? X squared minus 1. And you can factor that further, right? Old stuff, right? X plus 1 times x minus 1. What are your zeros?
2, negative 1.
2, negative 1, and 1. Perfect. Okay? Don't mess with calculus if you can do it simpler. Okay? But you can take derivatives, set them equal to 0. You can do all those things that you want to do, but this is the simplest way. Okay? Now this one cannot be found by elementary algebraic methods. So that one then set up for Newton's method, okay, to find the zeros for that. This particular function has only one real zero, and by using more advanced algebraic techniques, you can determine that zero to be, oh, of course, didn't you see that right off the top? Of course we did. The cube root of that thing with the square root inside and a fraction under the square root. Because the exact solution is written in terms of square roots and cube roots, it's called a solution by radicals. Okay. Guess what? I don't want to mess with that. Give me Newton's method any day over that. Okay. Whoa! And that's the last. And that's it. Okay. They have a couple of, I found rather squirrely drawings of a couple of young, bright mathematicians. Niels Henrik Abel, I can't remember where he was from, that sounds sort of like a Swedish or Norwegian or some sort of name, and Évariste Galois, French, I'm pretty sure. Galois was too smart for his own good. They were both brilliant mathematicians. I don't know how Abel died, but Galois was messing around with someone else's wife or girlfriend or something like that, and someone got challenged to a duel, and he got killed. So just because you're a bright mathematician doesn't mean you have any sense. I mean, no, that's not what that story means, but something like that. So anyway, two brilliant mathematicians that both died awfully young. 27 and 21. All right, if that's of interest to you. I think they did some of the work on solution by radicals, I assume. And if you read on there, you'll see another mathematician, Jerome Cardin, I think Italian, they say, published a method for finding radical solutions, blah, blah. So, yeah, Norwegian. Abel was Norwegian, so it's probably not how you pronounce his name. And Galois proved some other things with radical solutions. So those are interesting to you as paper topics, especially since this, one of my best classes ever. I've gotten one research paper in. Hint, hint. Hey, and what's next week? Spring break week. All right. What a wonderful time and opportunity to work on a research paper. Wow. Nice. Okay. Now, homework exercises here. Do either 3 or 5. They're both at Calc Chat. 3's at Calc View. Any of the odds 7 through 15, they're all at Calc Chat. 9's at Calc View. Do either 17 or 19, they're both at Calc Chat. Do 21. Has 4 parts to it. They're at Calc Chat. Do 23, it's at Calc Chat and Calc View. Do 25, it's at Calc Chat. 27, you can explore doing that if you'd like. It's at Calc Chat. And 29 and or 31, they're both at Calc Chat. And then 33 or 35, they're both at Calc Chat. True, false, 37 or 39, they both should be at Calc Chat. And 41 is at Calc Chat. All right. So that finishes Newton's method. Let's move on to differentials, 3.9. And the reason we need to do this, you're going to be using differentials for quite a while. And if I'm not mistaken, this is, the last section in the chapter. So I want you to be familiar with this. What we're going to be doing with it, I found to be a little on the lame side, but you'll be using differentials up through differential equations. You'll be using differential, and that's not what differential equations mean. That sometimes we use them for that reason, too. Actually, differential equations to me should be called derivative equations, but I didn't name them. So, let's move on to, we're still in Chapter 3, Applications of Differentiation. 3.9 is differentials. And we will, or the objective is to understand the concept of the tangent line approximation, compare the value of a differential dy with the actual change in y, delta y, estimate the propagated error using a differential, and find a differential of a function using differentiation formulas. Some of this we'll go through fairly quickly. Oh, well, maybe not. We'll see. So anyway, we're going to start with tangent line approximations. So let's start with a function, f. And we know it's differentiable at some value c. The equation for the tangent line, then at that point c, f of c, c is the x value, f of c, of course, is then the y value. And since it is differentiable there, that's going to be the slope, f prime of c. So we'll have y minus y1 is equal to m times x minus x1. We've seen that, the good old point slope formula. Slope being the first derivative at c, and the point c, f of c, being that. Well, you can move the f of c to the other side, and y is equal to f of c plus f prime of x minus c. Now that expression there, okay, is called the tangent line approximation or linear approximation of f at value c, okay? Because c is a constant, y is a linear function of x. So that's a value, that's a value, that's a value, and x is to the first power. So this is y being a linear value of x, okay, based on the first derivative. So if the curve's doing like this, you're basing it here. Let's see if they got a figure for us. Not yet. Hopefully they will. Yeah, they will in a minute. Okay. Moreover, by restricting the values of x to those sufficiently close to c, whatever that means, the values of y can be used as approximations to any desired degree of accuracy, just to get the x close enough to c, of the function f. In other words, as x approaches c, the limit of y is f of c. Of course, because that's what you know it is there. Okay. So, found the tangent line approximation of f of x is equal to 1 plus sine of x at the point 0, 1. Okay? 0 for x, 1 for y. you know that is the exact value right there. When x equals 0, sine is 0, 0 plus 1 is 1, so y is 0. So we're going to use the tangent line approximation at that point. Then we'll use a table to compare the y values of the linear function with those of f of x on the open interval containing x equals 0. Yeah, I can't wait. Okay. So what you reckon we're going to do first? Let's take a derivative. Let me get my pen color first. What's your f prime of x? Second?
Cosine of x.
Cosine x. All right. Now, let's go back. Here's our linear approximation. Okay? C is going to be 0, alpha C is going to be 1. Okay? C is 0, and alpha C is equal to, or alpha 0 is equal to 1. Okay, we already knew that from here, that point. Okay? So, reminding you, y is equal to alpha C plus slope times x minus c. Okay? So, y, this is the approximation, is equal to alpha of c plus alpha prime of c times x minus c. Okay? C is equal to 0, alpha c is equal to 1. So y is equal to 1 plus, we need to do this, alpha prime at 0. What is alpha prime at 0? Cosine of 0. 1, excellent. So that's just 1 times x minus 0. Okay, so this is 1 plus x. Okay, pretty simple formula there. Your linear approximation for this function close to x close to 0 is going to be 1 plus x. Okay? Now, it says use the table to compare those. Let's just go to their table. So, okay. We've already done this, but I'll go on and erase it. Okay. Derivative is cosine x. So the equation of the tangent line to the graph of f at the point 0, 1 is y is equal to alpha 0 plus alpha prime of 0 times x minus 0, which comes down to 1 plus 1 times x minus 0, which is 1 plus x. All right, we got there. Okay. Now they're going to do their table. Now, they picked some values pretty far away, and we'll do alpha of x is equal to 1 plus sine of 0.5. Now, guess where the 0.5 is measured in? In calculus, you'll almost always use radians, never degrees, unless for some reason they specify using degrees. These are going to be in radians, okay? So the 0.5 is not 0.5 degrees. Those will really be close because that's a really small value. So these are in radians, and if you plug that in, you see, there's your value, okay? Not too far off here, okay? But when you go to negative 0.1, you're even closer. Negative 0.01, I mean, way, way, way closer, okay? And at 0, of course, you're exactly that value. And then on the other side, you're off by 0.01, 0.1, and 0.5. So you're getting further and further off the further you go. Now, why is that true? Okay? Well, if you don't remember this from from trig, and you probably don't, or you may not, this is your sine function. It's just been elevated by 1. I mean, that's the original function. Vertical shift upward by 1. Normally, sine function would be down here, following the same pattern. Okay? But this is how I told you it helps remind me of what the derivative of sine is as cosine, because cosine at 0 is 1. Derivative of sine at 0 is 1. And that is almost a straight line. In between that, you can hardly see any blue at all. Get a little further out and you see a little bit of deviation of blue. And that's why when you got out to 0.5, which is pi force is still a little bit more than 0.75, so you're not very far off even there. Okay, so but certainly inside that you're very close. Your linear approximation is not bad at all. But of course, the sine is a curve, so once you leave the point, it is curving away from the point, okay, from the straight line approximation. But it's still very, very close, okay? Because this line here is y is equal to 1 plus x. That's your identity function here, slope of 1. You've just gone up 1. It's almost on top of the sine function for anything close to 0. Okay. That's all she did, okay? I guess that's fine. So let's then talk about what differentials are. And to me, this is sort of a jump. And you think, okay, what did that matter in terms of what a differential is? When the tangent line to the graph at a point C alpha C, here it is again, y is equal to alpha C plus sub prime of C times x minus C. Okay? Not just this tangent, the 1 plus sine function like we just did, but any old function here. When that's used as an approximation from the graph of f, the quantity x minus C is called the change in x. What we've named that? Maybe delta x, okay? Yeah, okay. So if you're moving from C to x, C plus delta x, you're moving from here to here, okay? Meaning on the graph, you're going from here to there. Along the tangent line, you're going to there. The actual function value is moving there. This is the error between the actual function value and the differential, or the tangent line value, okay? Now, this function here is, this is alpha C right there. That value right there is alpha C, okay? This difference here is how much this is moved. Well, that's the amount of the tangent line, the value of the tangent line, what slope that is, times your delta C here. That's your rise over run type thing. You've gone up that much for every amount you've gone there. This being rise over run multiplied by run, you got your rise. So that's what that is. And that is your tangent line approximation. Now, the actual function goes up to here, okay? That's the actual value of the function. So your delta y is that, okay? This is your delta y by the tangent line approximation, okay? So this is your alpha C plus delta x, and that difference is delta y. And, yeah, you plug in for your x, C plus delta x, and alpha of that is your y value. Rather awkward expression of it, but that everything they've done here is true. Okay. And again, at this point, I'm saying, okay, what is the point here? They're getting to it. when the delta x is small, okay, like very small, this one's pretty far out, so you do have some measurable error. But if you kept your delta x, say, within those, you don't have much error at all. Yeah, you got a little bit for sure. There's a little blue showing there, not as much here. But if you're anywhere in that delta x, your approximation is quite good. The further you get out, the more deviation you got from that, then your approximation is not as good. So when the delta x is small, the change in y, denoted by delta y, can be approximated by this. Your f of c plus delta x minus f of c. That is the actual change in y. The f at the c plus delta x minus that. Well, this is approximately equal to f prime of c times your delta x. Okay? So, what they're saying here is this thing, the delta y here, is approximated by the f c prime delta x, which is your tangent line approximation. Okay. Not perfect, but usually good, as long as your delta x is pretty small. For such an approximation, the quantity delta x is traditionally denoted by dx, okay, and it's called the differential of x, okay. Now, this is the part that sort of grates me, okay, because to me, the dx is the delta x as the difference is getting very small. But here the dx is being kind of given a different name, though that is ultimately what it stands for. So this comes out being the approximation, that's the actual value, and the deltas are in there, and you've lost the delta down here. And that's what kind of drives me a little nuts. I don't know why it does, but it always has. The expression f prime dx is denoted by dy, which again is to me, that's the limit. As the delta x is going to 0, then your delta y is also going to 0, and that's called the differential of y. Okay. So here's your definition of differentials. That y is equal to f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-zero real number. Okay? So it can't be 0. Any non-zero real number, differential of y denoted as dy, is then dy is equal to f prime dx. Okay. In many type of applications, the differential of y can be used as an approximation of the change in y. Okay? So therefore, the delta y is approximately equal to the dy. Remembering this is the exact one, that's the approximate, which to me is backwards because, you know, that should be the limit as this is getting close to 0, but that's not what it means. So your delta y is approximately f prime of x dx. Okay. So I hope I'm not messing you up by telling you how much it writes me. Okay. So here's example 2. All right. Let y equal x squared. Good old function. Okay. Find dy when x equal 1 and dx is equal to 0.01. Okay. Hint, hint. Here's what dy is, f prime dx. Okay? Now, if you want something to sort of think of this as, and this is where my thinking sort of deviates from theirs quite a bit. Remember, we used to call dy dx y prime, right? Which, if y is a function of x, that was the f prime of x, right? Now, this isn't what you're doing, of course. Mathematicians would go squirrely if you say this, multiplying both sides of the equation by dx. And you have dy is equal to f prime dx. Now, once you get into things like integration and different techniques of integration, you're going to do this all the time and think nothing of it, okay? In differential equations, when you've got separable equations. You're going to do this, and you're not thinking in terms of differentials now and these being approximations. You're thinking of these as being the real thing, okay? And so ultimately, we're going to get away from this. One is an approximation of the other. They're doing the same thing. But right now, they're doing two different things, okay? So here, find dy, which is the approximation, I think it is, when x equal to that, and dx is equal to 0.01. X equal 1, okay. So what are you going to have to do? You're looking for dy. What was the definition of dy? F prime of x dx. Okay? So what's one thing you're going to have to do? Take a derivative. So I hate to use it. Let's just call it y prime. No, let's call it f prime. Okay. To use their nomenclature. Okay. F prime of x is equal to 2x. Okay. So dy is equal to 2x. It's f prime, that's for sure. But why write that down again? Okay. 2x times your dx. Okay. And what is your x? So this will be 2. And what's your dx? 0.01. So your dy, which your approximation of the difference in y, is 0.02. Okay? Now, let's compare that value with your delta y when your x equals 0 and delta x equal 0.01. Your delta y is the actual change of y, which would be f of x plus delta x minus your f of x. Okay? Now, did we calculate what f of x was yet? I don't think so. That's pretty easy. What's f of 1? That's 1. Very easy. Okay? Now, your x plus delta x is equal to what? 1 plus 0.01, which is 1.01. So your f of 1.01 minus your f of 1. Well, pull out the calculator and do 1.01 squared. That's what f of 1.01 is. Some of you may be able to do it in your head. What is that? 1.01 squared. Okay. Minus, and what was your f of 1? You just told me? 1. So this would be 0.0201. And what's the difference of those two? 0.0001. Pretty close, okay? That's the exact value. This is your differential value. Okay. Does that make sense? Oh, I was looking on the wrong page there. Yes. Now, can I erase? Okay. So let's see how they did it. Because y is equal to f of x, that's x squared. F prime would be 2x. Differential dy would be dy is equal to f prime dx. F prime is 2x. times dx. The F prime of 1 would be 2 times 1 is 2 times 0.01. So that dy here, meaning your differential of y, is 0.02. Okay. Your delta x, 0.01, same as before. The change in y then would be, the actual value change would be f of x plus delta x, which is 1.01, right, minus f of 1. Okay, f of 1.01 minus 1, and that would be, like you said before, 1.0201 minus 1 would be 0.0201. Okay. And here's the figure that shows that. The actual change of your y is your delta y from 1,1 to 1.01. There's the actual change of y, that's your delta y. Your dy, which is dx, or y prime d, which is your slope times the delta x, okay, that takes you out to here. That value, this is then the difference between the two, okay? This is your dy, that value there, and your delta y is, you want the actual function value. Any questions? All right. Well, that's all that you have there. I thought they were going to show the table, but they don't. You can do the table if you'd like. It just shows how the error does grow. And that's what we're talking about next, is error propagation. 3 minutes? 8 minutes, okay. Let's see what we can get done in 8 minutes. Okay. If you let x represent the measured value of the variable, and let x plus delta x represent the exact value, okay, then delta x is the error in the measurement. I've always thought of that as the reverse of that for some reason. Okay? Because it seems like to me your sign is wrong here. But maybe I'm wrong. Okay. Finally, if the measured value x is used to compute another value of f of x, then obviously you got something wrong there because you're using something that's not true. Then the difference between the f of x plus delta x, which they say is the true value, and f of x is the propagated error. Now, this part makes sense, okay? This is the exact value of the measurement, and f of this minus f of the measured value, that would be your error that propagated from the fact you're not using the exact value, okay? Because you're doing a function on the using this when you should have been using that, but you didn't have that because that the measured value is all you've got. Okay, so you've propagated the error delta y. Okay, so the measured radius of a ball bearing, this is example 3, is 0.7 of an inch. Okay, it's shown in the figure below. The measurement is correct to the nearest hundredth of an inch. Estimate the propagated error of the volume of the ball bearing. Okay. Now, do we have time to do this? Think so? Huh? 5 minutes. All right, let's see if we do. All right. The measured radius is 0.7, but the measurement is correct within 0.01 of an inch. Here's the problem, folks. We don't know which way. We don't know if this is where the actual value is 0.71 inches or 0.69 inches. We know that the measurement is correct within that, okay, or something in between. Estimate the propagated error in the volume of the ball bearing, okay? So, what is the volume, by the way? Remember that formula? Volume of a sphere? 4/3 pi r cubed. Volume of a sphere. Quite often, in some math books, there'll be front, inside, or back cover, not on the front inside. Let's see, I think maybe, yep, back inside cover, no, I'm wrong. No, here it is, yeah, sphere, volume 4/3 pi r cubed, okay. Now, estimate the propagated error in the volume of the ball bearing, okay? Now, our formula here, the propagated error is your delta y, which is the difference between the two, okay? So, delta y, I'm going to call it delta v. Is that okay? That's what we're estimating, the propagated error in the ball bearing. Okay, this would be f of x plus delta x, that's the exact value. We really should be saying plus or minus, okay, because the measure is correct within that, and we don't know. So this would be f of x plus or minus delta x minus f of x, okay, where x is your measured value and this is your propagated. I mean your how much you're off by. Okay, so that is what we're trying to estimate here. Okay, so your delta V here is then, let's do the plus side first. It would be 4/3 pi, and that would be 0.71 cubed minus f, well, 4/3 pi 0.7 cubed. So if someone does have your handy dandy calculator available, let's see what your propagated error would be. You can factor out the 4/3 pi and deal with that, if I could write it, 4/3 pi, and then do 0.71 cubed minus 0.7 cubed. Anyone do that fairly quickly? 0.6245. That's probably, huh? Okay. Okay. What was that the answer to? Just the difference between those two? Oh, okay, sorry. I'm sorry. I missed the word estimated. We were actually taking the difference, okay? When you estimate the difference based on what we did before, the delta V is approximately equal to F prime. Go back to your, this, where is it? Yeah, F prime times dx, okay? So this would be F prime of x times dx, where the dx is the plus or minus 0.01. So the approximation of this is, what is your f prime? If this is f, what is f prime? Equal 4 pi r squared, which is sort of interesting in its own right, and that is exactly the surface area of the sphere. What? You know, it just happens to be exactly that. So we'll take this and plug in, but the r we're going to plug in 0.7, so this will be 4 pi times 0.7 squared times our 0.01. Okay, and that will be 4 pi times 0.49 times 0.01. All right. Please use the calculator. I don't want to do that one in my head.
.06158.
06158. You said something like that?
Right.
That's exactly what they got in the book. Okay? Now, what they then sometimes will refer to is what they call relative error. Are we out of time yet?
Yes.
We are. Okay. We'll pick up with relative error next time. Okay? And we usually think the relatives have pretty much error, don't we? Okay, never mind. We won't go there. All right. Homework exercises here. I think you can do 5, any of the odds 5 through 9. They're all at Calc Chat. 7's at Calc View. 11's at Calc Chat. Any of the odds 13 through 17, they're all at Calc Chat. 13's at Calc View. And any of the odds 19 to 27, they're all at Calc Chat. 23's at Calc View. 29, Calc Chat. 31, Calc Chat. And you can start doing 33 if you'd like. It's similar to the one we're working on now, but we have a quite good deal. We'll catch you Wednesday. And I'll try to have, well, your test will be ready on Wednesday. Okay.